Okay, let's just dive right into this. Today, we're unpacking a really comprehensive CSS General Science and Ability Study package, and we're focusing entirely on atmospheric hazards. Look, whether you're aiming to absolutely crush a high-level exam or you're just trying to wrap your head around how our changing climate is driving this extreme weather, getting a grip on the mechanics behind these massive atmospheric events is, well, it's absolutely crucial. So in this explainer, we're going to break down the actual scientific engines that drive our planet's most violent storms, and then we'll look at how human societies can actually step up to mitigate their devastating impacts.
Here's the blueprint we'll be following today to build out your mental model. We'll start with a quick overview of atmospheric hazards, then move through tropical cyclones, tornadoes, and weather fronts. After that, we'll do a comparative analysis of their impacts, and finally, wrap up with mitigation and the way forward. Let's get to it.
All right, Part 2, Tropical Cyclones, Scientific Mechanisms.
To kick things off, we really need to clear up the taxonomy of these massive oceanic storms. You might be wondering, what's the actual difference between a hurricane, a typhoon, and a cyclone? The answer? Absolutely nothing but real estate. The critical variable here is simply geographic location, not the mechanism itself. They're all the exact same meteorological phenomenon, a wildly powerful rotating storm centered around a low-pressure eye. So if you're in the North Atlantic or Northeast Pacific, you call it a hurricane. Over in the Northwestern Pacific, they're typhoons. And down in the Indian Ocean and Southwestern Pacific, we call them cyclones. It's literally just a regional naming convention, but the physics are identical.
Now, if you need a solid exam-drawable model for cyclogenesis, how these storms actually form, it basically comes down to a 6-step recipe. The primary engine here is latent heat, and for that you need warm ocean waters, specifically anything above 26.5 degrees Celsius. When you combine that giant pool of warm water with atmospheric instability, you get moist air rising rapidly. Next, you need the Earth's rotation, the Coriolis effect, to kick in and induce that signature cyclonic spin. Add in low-level wind convergence that piles up the air, a pre-existing disturbance to act as a seed, and finally an upper-level outflow. That outflow acts kind of like an exhaust pipe, radiating the excess heat away from the system. When all 6 of these conditions align perfectly, a monster is born.
So how do we actually quantify that destruction? We use the Saffir-Simpson Hurricane Wind Scale. It classifies these storms from Category 1 up to Category 5, and it bases that rating entirely on maximum sustained wind speeds. Now, what's really interesting and terrifying is that once a storm hits Category 5, meaning winds are exceeding 157 miles per hour, we aren't just talking about a few missing shingles anymore. We're talking about catastrophic structural failure for framed homes, power grids being completely wiped out for weeks or even months, and entire coastal areas becoming virtually uninhabitable.
Moving right along to Part 3, Tornadoes, Anatomy of Destruction.
By definition, a tornado is a rapidly rotating column of air that extends from the base of a thunderstorm all the way down to the ground. I want you to contrast that massive, sprawling oceanic span of the cyclone we just looked at with the incredibly tight, ground-level funnel of a tornado. While a monster cyclone might max out around 150 to 200 miles per hour, a tornado's tightly concentrated wind speeds can exceed an astonishing 300 miles per hour. That intense concentration makes them some of the absolute most violent weather phenomena on the face of the Earth.
So how do they form? Tornadogenesis usually kicks off inside severe supercell thunderstorms. First, you've got your thunderstorm instability and lift. Then, you introduce wind shear. That's a change in wind speed and direction as you move up in altitude. This shear creates a rotating horizontal tube of air, which the updraft then grabs and tilts vertically, creating what we call a mesocyclone. Next up, a rear flank downdraft plunges down and interacts with that updraft. And finally, we get vortex stretching. This is where the physics get wild. Because of the conservation of angular momentum, as that rotating column is stretched vertically and gets narrower, its spin rate increases exponentially, eventually forming that iconic funnel cloud that touches down.
Historically, meteorologists measure these storms using the Fujita scale, but the original F scale had some pretty glaring limitations. For one, damage assessments were highly subjective. Plus, wind speeds were merely estimated after the fact rather than scientifically measured. And crucially, the scale completely failed to account for the massive variability in how different buildings are actually constructed. I mean, think about it. A poorly built, drafty old barn blowing over simply shouldn't yield the same storm rating as a heavily reinforced concrete structure being torn apart, right?
To fix that and ensure real scientific accuracy, meteorologists upgraded to the enhanced Fujita, or the EF scale, back in 2007. This scale ranges from EF0 to EF5.
When you hear a storm gets an EF5 rating, that implies winds over 200 miles per hour and, quite frankly, incredible damage. At this extreme end of the scale, strong, well-built frame houses are literally lifted entirely off their foundations and swept away. We're talking about forces so strong that automobile-sized debris can be thrown through the air for well over 100 meters. It's just staggering power.
Okay, shifting gears to part 4, weather fronts and mid-latitude cyclones.
Let's talk about fronts. Fronts are simply the battleground boundaries between opposing air masses. Take a cold front, for example. This features cold, incredibly dense air aggressively wedging itself under warmer air. Because of its steep slope and fast movement, it violently lifts that warm air up, triggering heavy precipitation and severe thunderstorms. Now contrast that with a warm front. Here the warm air slowly, almost gently glides up a slope over colder air, which usually results in widespread, steady rain and overcast skies. And if neither air mass is strong enough to actually push the other out of the way, well then we get a stationary front, bringing persistent, lingering precipitation that just seems to hang around forever.
So the absolutely crucial point here is understanding what happens when these fronts interact dynamically. An occluded front forms when a fast-moving cold front actually catches right up to and overtakes a warm front. It essentially pinches the entire warm air mass off the ground and lifts it aloft. Now, definitely take notes on this because it is an essential CSS exam concept. The formation of an occluded front marks the absolute peak intensity of the storm and simultaneously signals the beginning of the eventual decay of these mid-latitude systems.
Let's tie that all together into the full mid-latitude cyclone life cycle. It's basically a continuous story of atmospheric instability desperately seeking equilibrium. It begins with cyclogenesis, a little wave forming along a temperature gradient like the polar front. It then intensifies into the mature stage where you have those distinct warm and cold fronts we just talked about and plummeting central pressure. Then comes occlusion, where the cold front violently overtakes the warm, effectively cutting off the storm's main energy supply. Finally, we reach dissipation. This happens as the temperature contrast levels out, drops to zero, and the storm's driving force completely vanishes.
Which brings us to part 5, impacts and analysis, a comparative assessment. To really synthesize all this for an exam, we have to step back and ask, how do these atmospheric giants actually compare in their scale, their duration, and their specific methods of destruction? Keeping this analytical question in mind is going to help us actively categorize the massive amounts of meteorological data we've just covered.
Let's do a direct side-by-side comparison. On one hand, tropical cyclones are these sprawling oceanic titans. They span hundreds of kilometers, they can last for days or even weeks, and they derive their primary destructive power from massive coastal storm surges and widespread inland flooding. On the exact opposite end of the meteorological spectrum, tornadoes are violent, land-based anomalies. They span mere meters to maybe a few kilometers, they last only for minutes or hours, and they deliver absolute, highly localized destruction entirely through extreme wind speeds and flying debris.
Yet, despite their totally different mechanics and lifespans, they share a pretty grim reality. They're cascading impacts. Whether you quantify it by the EF scale for tornadoes or the Saffir-Simpson scale for cyclones, the human and economic cost is universally devastating. We're talking catastrophic structural destruction, immense agricultural devastation that can lead to food shortages, massive economic disruption through interrupted supply chains, and of course, profound social displacement and psychological trauma for the communities caught in their paths.
Finally, part 6, mitigation, the way forward.
So what do we do about it? Well, practical structural engineering and forward-thinking planning can actually save lives. Effective disaster risk reduction requires a massive, multi-pronged approach. We absolutely need the implementation of advanced early warning forecasting systems to buy people precious time. We must aggressively enforce stronger, modernized building codes that can actually withstand these higher wind loads. Furthermore, comprehensive emergency response plans and widespread public education campaigns are totally vital. We have to ensure communities know exactly what to do the second the sirens sound or the evacuation orders are given.
Okay, to synthesize everything we've covered today into high-yield takeaways, here are 3 powerful, quotable conclusions derived directly from our analysis. These are perfectly structured for capping off a killer exam response. Number 1, atmospheric instability is the ultimate engine of severe weather. Number 2, geography dictates the scale, but mechanics dictate the destruction. And number 3, mitigation is what bridges the gap between a natural hazard and a human disaster.
I want to leave you with this final provocative thought. We've seen the raw power of cyclones, the violent, localized speed of tornadoes,
and the vast, clashing engines of weather fronts. As our meteorological forecasting technology improves, giving us clearer and earlier warnings than ever before, the critical question remains: will our infrastructural resilience and societal planning evolve fast enough to withstand the Earth's most violent atmospheric engines? Thank you so much for joining me for this explainer. Keep analyzing, keep studying, and as always, stay curious.